Hi, welcome to the 8th session on inner product spaces and the second session on Gram-Schmidt process. In the first session on Gram-Schmidt process, we looked at a two-dimensional real inner product spaces and constructed an orthonormal basis. What does it mean? It's a basis consisting of each vector is of unit norm and each of the vector is perpendicular or orthogonal to the other. Okay, right. Now we want to generalize this to any inner product space even over complex numbers. The basic trick is, now we had understood the geometry of what is meant by orthogonal projection and how do we get the vectors, vectors which are mutually perpendicular to each other. This is the trick. Okay, I hope you all enjoy it and you really find it's very easy. Okay, just because geometry is clear in our mind. Okay, let's get started. So this is as usual, this is my channel, this is the email ID. You can download the list of videos from here or you can scan this. What is the advantage of having the list of videos? It gives you description, it gives you URL, it also gives references, and also, for example, inner product spaces, this is the 8th lecture, all of them will be ordered in the fashion so that you know where to start. Okay, that's the advantage. Okay, let us quickly start the problem. So let V be an inner product space possibly over R or RC. Okay, it does not matter where we are. Okay, you will see that it's a complex conjugate. Okay, the other variable, second variable, etc. will not appear. Everything is easy. So what are the things I want you to remember? Suppose V is a vector. Okay, V is a vector, non-zero vector, and X is any vector in this. Okay, I will always draw a picture like this. This is my X and this may be my this is my V, this is my V, this may be my X, and I want to orthogonally project it on this. Okay, so orthogonal projection we denote by Px of V. What is this by definition? Let us recall, this is V minus, you project this. Okay, the orthogonal projection is X inner product V by norm V squared into V. Okay, just ignore all these things. This is the orthogonal projection. Okay, this is this vector P V of X. Right, what do we have learned? So this is the first definition, recall this, and second thing you should recall is this, X minus Px of V. Okay, this inner product with V is 0. That is, X minus Px of V is perpendicular to V. That is this object. Sorry, this is not a good thing. This may be my X minus PV of X. Again, I am writing wrongly, PV of X. Orthogonal projection. Okay, remove the orthogonal projection. Right, these are the only two facts I will need. Now let's assume V1. So let's assume this space dimension is n. Okay, let V1 to Vn be a basis V. What do we want to construct? Idea is to construct an ON, that is orthonormal basis. Let me see whether I had switched on the recording. Yeah, it's on. Okay, and also I'm sharing, right? Yeah. Basis. What does it mean? That is, I want to construct a basis U1 to UN so that norm of Uj is 1 for all j, and inner product of Uj with Uk is 0 for j not equal to k. If you know the Kronecker delta, then Uj Uk inner product must be delta jk. This is called Kronecker delta. That means delta jk equal to 1 if j is k and equal to 0 otherwise. Okay, this because you should learn some jargon also on the way, right? Okay, right? Okay, now we want to do that. So the first thing, let us set up to make my life easy. When I want to project some vector x in b, okay, onto bj component, okay, so instead of pbj of x, I will write as pj of x, right? So that I do not write pj of x. And what is pj of x? This is x inner product bj and norm bj. Now notice that bj's are all elements of a basis, therefore none of the bj will be 0. Therefore I can write it in the denominator inner product bj because it will not be 0. Is that okay? Right. So how do we do that? Let's say go through. See again, so far I have not used whether it is inner product over R or C. You will see that I am just using inner product symbol only. Right? Okay. Now let's go to the next one. Okay. So what we do? So I will take w1 equal to v1. So I don't change it. No change at all. Okay. Now I want to do w2. Now recall how do you do that? So let me just write this as v1 and this is my v2. Then what do? I want w2 that should be orthogonal to w1. That is, it should be orthogonal to v1. And do you know how to construct it? Yes, you know how to construct it. How do you construct? From w2 you take away p1 of w2, right? Just in case you had forgotten, this is w2 minus w2 v1 by v1 and this inner product v1. Okay, w2 inner product v1 will be this, and this will be w2 v1 minus w2 v1 v1 therefore it's a w2 v1. Is that okay? Therefore it is 0. So did I use it's a real inner product or a complex inner product? Nothing, because this we have checked for any inner product, okay, be it real or complex. Is that clear? So I got a w2. Okay, now what do I have? From v1 v2 I got a w1 w2. What is w1 is this. What is w2? As defined, right? And what do I know? I know w1 and w2 are orthogonal to each other. Okay, now can w2 be 0? Suppose w2 is 0, go back to the definition. What does it mean? This is w2 my some scalar times v1. Oh sorry, again v2, here I wrote correctly v2 v2 w2 is v2 minus p1 of v2. I'm sorry for the goofing. Again let's quickly look at that. What is my w2? w2 is v2 p1 of v2, that is v2 minus v2 v1 by v1. Okay, and what did we check? w2 and w1 is 0. That is same as saying w2 v1 is 0. Okay, just now we checked it. Okay, right. Now can w2 be 0? If w2 is 0, do that, what do you get? You see, this is 0, right hand side is 0. That means v2 is a scalar multiple of v1. That means v1 and v2 are linearly dependent. But where do v1 and v2 come from? They come from a basis. Therefore, it cannot happen. Do you understand? Therefore, this cannot happen. Therefore, w2 is not 0. Right? Now let's look at next one. See, notice that w2 belongs to the linear span of v1 and v2. Yeah, because look at that. What is w2? v2 minus scalar multiple of v1, right? And w1 is also there because w1 is nothing other than v1. You understand? Therefore, what do I conclude? Span of v1 v2 and span of w1 w2. Okay, so this contains this because W1, W2 belong to this. Is that clear? Now what is the dimension here? Dimension is 2, right? And remember the third fact I needed, I should have said that, I forgot. Yeah, third fact here is if W1 to W are non-zero vectors so that Wi, Wj is delta Ij, then this is linearly independent. This we saw in the last lecture, right? Okay. Therefore, let's come back. So what do I think I have concluded? So this dimension is also 2. Are you following? Dimension of this fellow is also 2, and that's a subspace of this space which is of dimension 2. Therefore, equality holds. You understand that? That is span of W1, W2 is a vector subspace of V1, V2. Since this is linearly independent, this dimension is 2, and since W1, W2 are non-zero and orthogonal to each other, we had already seen any orthogonal set consisting of non-zero vectors is linearly independent. Therefore, this dimension is also 2. Therefore, we have these two are equal. Okay, pause, review, proceed. So now how do I define W3? Remember, W3 must be perpendicular to W1 and W3 must be perpendicular to W2. Now how do you think I will get it? I should get it from V3. How will I get it from V3? Remember, in R3 with the dot product, okay, if I have A, B, C, okay, so call this as vector X, then X dot E1 will give me A and X dot E2 will give me B. Therefore, if I throw away from the vector X, X dot E1 plus minus X dot E2, what I will get will be 0, 0, B, which will be perpendicular to E1 as well as perpendicular to E2, right? So the same thing. So what, as I said in the picture earlier, okay, I am taking V3, projecting onto the W2 and W1 component. Okay, therefore from V3 what do? I start with P1 of V3, right, minus P2 of V3, where P2 is the projection with respect to W2, not with respect to V2. You understand that? What is P2 of X? This is X W2 and W2 by W2 W2. You understand that? Okay. Now this is my W3. So again, to think geometrically, from V3 I am taking out the W1 component. I am also taking the W2 component, not V1 V2 component. Okay. Then what I get should be perpendicular to as W1 as well as W2. Right? That's it. Notice that this is some scalar multiple of W1. This is some scalar multiple of W2. Are you following? Because that's a crucial thing I want to do. Therefore, W3 inner product W1, what is it? Some scalar okay, right? This is, I want to say this is 0. Therefore, it is V3. What do I have? I have W1 minus P1. What is P1? That I know. That is nothing other than V3 W1 by W1 W1 W1. Okay, and inner product W1. Next will be V3 W2 minus W2 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 inner product W1, because I am starting with W3. You understand? Now let us look at this, right? This one get cancels. Therefore, I have W3 V3 minus W1. Okay, they add up to 0. And this fellow W1 and W2 are orthogonal to each other. Therefore, this fellow is 0. Therefore, this term is also 0. Therefore, I have proved this. Right? Similarly, if I take a 2, I'll put a 2 here, 2, 2, and I'll have a 2, right? Therefore, this will be 0. Are you following? W3 minus W2, sorry, inner product W2 will be V3 W2 minus V3 W1 by W1 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 W2, right, minus V3 W2 by W2 W2 inner product W2 W2. You follow that? And this is 0 and this cancels, so I get this equal to 0. Are you following? So what I have shown, so from V1 V2 V3, okay, I have constructed W1 W2 W3. okay, this is orthogonal, okay, set of non-zero vectors, because we already saw W1 W2 W3 are non-zero and they are mutually perpendicular. They are not orthonormal. I am not claiming they are orthonormal. Do you understand that? They are just simply orthogonal to each other, right? Therefore, this set is linearly independent, right? So, like last time, therefore, span of W1, W2, W3. Remember, okay, if I have W1, okay, then that belongs to span of V1, V2, V3, because I already know W1 and W2 are here. Right, it's in the span of V1, V2. Now let's look at W3. Now what is W3? W3, as we saw, is a linear combination of V3, W1 and W2. But W1 is nothing other than V1. But W2 is a linear combination of V1 and V2. You understand that? Therefore, this W3 is a linear combination of V1, V2, V3. Right? And we know W1, W2 already belong to span of V1, V2, and hence in the span of V1, V2, V3. Therefore, what is the conclusion? Therefore, span of W1, W3 is span of V1, V2, V3. So, understand this. If I understood this much, the rest is very trivial induction. We will do that. Okay, please stop, go through how we constructed W2, how we constructed W3. Important thing is W3. Okay, because when I constructed W2, I simply have to project onto the W1, which is nothing other than V1. But when I wanted to construct W3, I have to project V3 onto W1 and W2. That is, I have to subtract from V3 W1 component and W2 component, not V1 V2 component. Keep that in mind, because W1 W2 are already orthogonal. That is why I can construct whatever I get as W3 is orthogonal to W1 as well as W2. Okay, this is the beautiful geometry. Understand that. Okay, now induction hypothesis, we will do that. Okay, assume that for okay k less than n and greater than or equal to 1, okay, we have constructed W1 to Wk such that 1, the W1 to Wk is an orthogonal set of non-zero vectors. That non-zero vectors actually will follow later also. Orthogonal, what does it mean? For I not equal to j, or for I and j, Wi inner product Wj will be delta Ij, where I and j run from 1 to k. And what is the second one? The second one is the span of W1 to Wk is same as the span of v1 to vk. We are done it for 1, 2, 3. Up to 3 were shown. But for induction, it's enough if I was done for 1. Even 2 is good enough. But I just wanted to understand the geometry. That's why I went slow. Is that clear? Make sure you understand this induction hypothesis carefully. This is usually not well written, so you may get confused. So at kth stage, I already have vectors w1 to wk. What are the properties? This set w1 to wk is each one of them is non-zero and they are mutually orthogonal to each other. And second thing is they span a space. It's okay. That space is nothing other than span of v1 to vk. Therefore, okay, k-dimensional vector space bound. Is that all right? Okay. Now what is by induction I have to do? I have to construct a wk plus 1. How to construct? I am sure by if you have followed what I have said so far, you should know. How do you think I should do wk? Yeah. What do you have to do? Take vk plus 1 and what do? You orthogonally project vk plus 1 onto w1, onto w2, onto wk. Okay. Compute that w1 component, w2 component, wk component and throw it out from vk. Subtract it from vk. Then I get a wk. And I expect that wk will be non-zero and further it will be orthogonal to w1 to wk. Is that clear? Isn't it easy? Okay. So don't watch the video now. Pause it. Try to do it on your own. Write down. Okay. The definition of wk plus 1. This will give you immense confidence. Yeah. Try it. In case if you struggle, the video you can again follow. Right? Do it. So how do I construct? So wk plus 1 is vk plus 1 and minus p1 of vk plus 1 minus pk of vk plus 1, where pj of vk plus 1 is nothing other than p of wj of vk plus 1, that is vk plus 1 wj by wj and wj. You see that? If you do such things, it becomes automatic. You don't have to remember. Okay? Is that clear? Okay. Now the first thing is wk plus 1 is non-zero. Why? Suppose 0, as usual, vk plus 1 will be a linear combination of this is w1, wk, right? But the w1 to wk lies in the span of v1 to vk, right? You understand that? Therefore, vk plus 1 will lie in the linear span of v1 to vk. Do you understand this? If wk plus 1 is 0, that implies vk plus 1 lies in the span of w1 to wk. Notice that? But this we know by induction hypothesis, this is the span of v1 to vk. That means what? Vk plus 1 is a linear combination of vk to v1 to vk. This is a contradiction. Right? Why it's a contradiction? Because v1 to vk is a subset of v1 to vn, which is linearly independent set. And remember, my k is strictly less than n. Therefore, you want to assume vk plus 1, it will be at most n. K plus 1 may be at most n. At most, it may even be less. Are you following? Just learn to think. Okay, therefore it's non-zero. Then suppose 1 less than equal to j less than equal to k. Right? What do I have to prove? I have to prove wk plus 1 and wj is 0. But that's very easy. What is w? So this wk plus 1 inner product wj is vk plus 1 minus pj of vk plus 1 inner product with wj. Okay, so let us write it as pr r equal to 1 to k, because this j is fixed now. Okay, fixed j. Okay, but what is this? This is vk plus 1 inner product with wj minus, okay, this again, do you remember my trick? Think of this as ordinary product, therefore pk plus 1 wg and r equal to 1 to k. Now notice that this is, okay, a multiple of wr, right? Therefore some multiple times inner product wr wj. Okay, so then there is only one thing survives, r is a running variable, right? So unless r equal to j, then some scalar multiple wr wj will be 0. Therefore what is left out? The only thing which is left out is r equal to j term. Therefore this fellow is vk plus 1 inner product wj minus pj of bk plus 1 wg. Yeah, but what is this object? This object we know is vk plus 1 wj by wj and into wj. This is this object inner product with wj. So this cancel, therefore this is 0. Yeah, this is a scalar that comes out, this is a scalar that comes out, therefore inner product wj, but there is a denominator wj, therefore they get cancelled. Therefore, is that all right? So what do you think I have proved? Therefore w1 to wk plus 1 is an orthogonal set, non-zero vectors, right? Therefore this is linearly independent, right? Now again notice that wk plus 1 is lies in the span of v1 to vk plus 1 and w1 to wk lies in the span of vk to vk, therefore it lies in the span of v1 to vk plus 1, right? Therefore what do you think I have proved? I have proved span of w1 to wk plus 1 equal to span of v1 to vk plus 1. How did I prove that? Because this is linearly independent and therefore dimension will be k plus 1, whereas this dimension is k plus 1, right? And therefore this is a subset of that, therefore they are equal. It's the same logic as you have done. Okay, so now by induction out of 1 to n I have done, therefore, okay, by induction we have produced vectors w1 to wn in V such that 1 w1 to wn is an orthogonal set of non-zero vectors, but non-zero vectors will actually come from the second one, and the span of w1 to wn equal to span of v1 to vn. But let us we know v1 to vn is a basis, and w1 to wn is also has exactly an element and its span is same as this. Therefore what do I conclude? You understand that this is n vectors, these are n vectors, this is the dimension, okay, and these n vectors span this. So what is the conclusion? w1 to wn is a basis. Are you sure about this? Make sure you are understanding. Yeah, if I have an n-dimensional space, if I have some vectors, let us say something, okay, u1 to un, which span the space, then u1 to un should be linearly independent as well as it must be a basis. Okay, but we had already shown it's a linearly independent, but what we are showing it's actually a basis, right? Because remember w1 to w1 they are all mutually orthogonal, they are non-zero. Since they are non-zero, we know they are linear, that set is linearly independent. Therefore this is the set w1 to wn is a set which is linearly independent having n elements, but the dimension of the space V is n. Therefore w1 to wn must be basis. So there are a lot of ways of seeing. Okay, try to think. Okay, so what do I know about this? w1 to wn is an orthogonal basis. Now how do I get orthonormal? Remember, these are all basic elements, therefore W1, W2, W1 are non-zero, therefore define Uj to be Wj by norm of Wj, right? Then Uj is always 1 for 1 less than or equal to j less than or equal to n. And what do I know? And Uj and Uq, this is norm of Wj and 1 by norm of Wr and Wj Wr. Is that okay? And if j is not equal to r, then this is 0. If j equal to r, this is Wj Wj, and this is also Wj, this is also Wj, therefore 1 by norm Wj squared, that cancel, therefore I get 1. So this is delta jk. You understand that? Therefore u1 to un is an orthonormal basis. That's it. We proved it. How did you like the proof? Isn't it easy? Because the geometry helped us how to write the expressions, and we also know how to do that. The most crucial thing is look at the way the induction hypothesis is formed. Okay, when you want to learn, please go through it twice. Okay, our assumptions at the kth stage, what is our assumption? I considered W1 to Wk, and this set has two properties. What is the two properties? None of the Wj is 0, and that set is the Wj and Wk are orthogonal to each other if j is not equal to, Wi and Wj, for I not equal to j, they are perpendicular to each other, right? It's an orthogonal set of non-zero vectors. Second thing is most very crucial. That's why I built up V1, V2, V3 and W1 to W3. I went slowly. What did we show? The linear span of W1 to Wk is exactly the linear span of V1 to Vk. Alright, you understand the proof? Please go through it. At least go through twice. You will be surprised. At any time you can give the proof. Okay, I hope you enjoyed it. We will meet again.